Hello, everyone. In this lecture or in this discussion, I'm going to consider several problems in this book, chapter 2. Right now, we have been discussing chapter 2 for several lectures now, and I think we can finish chapter 2 after we have discussed these problems. So, as the end of chapter 2, I am going to consider several problems from the book. So, I will try to discuss about six problems. Example, they are actually examples in the book, but we will, you can find out the answers in the book also, but we will look at in a different angle in some problems with more details. So, example 2.170, 17, 2.18, 2.19, 2.26, and so on. We will try to cover all these things within about 1 hour. So, let's look at the first problem. Is example 2.17 in the book. In our lecture, this is the 13th lecture, therefore, this is example 13.1. Right. So it's about safe turn wait time. A truck requires 10 seconds to turn at an intersection onto a busy street. Assuming that the time between two passing cars follows an exponential distribution with the average time 3 seconds, what is the median time required to make a safe turn? Use simulations to find the answer. Right. So, a truck has to turn at an intersection, but cars are passing by. Uh, the time between these passing by cars can be assumed as exponentially distributed with average time equal to 3 seconds. So, the question is, what is the median time required for the truck to wait to make a safe turn? That is the question. So, we can answer this question theoretically, but here uh, it is asking us to get the answer approximately using simulations. So, to understand what we really mean by here, for example, let us consider a situation. Suppose the cars are passing by and the time between two cars is exponentially distributed with mean 3 seconds, right? So, for the exponential distribution, usually the parameter is the rate parameter. We denote it by lambda, right? Uh, we say, for example, a random variable x has an exponential distribution with parameter lambda. This is called the rate parameter. And we know that expected value of x is equal to 1 over lambda. So this is given as 3 here, 3 seconds. So therefore, lambda has to be 1 over 3. Right? So that's what we are going to use. We are going to assume that the time between cars is exponentially distributed with lambda equal to 1 over 3. So just to understand the scenario, let's look at now some random numbers. I have generated some random numbers from this exponential distribution with rate equal to 1 over 3, right? So my first time was from 0, and then we are starting from 0, and then the first car passed according to this observation at 0.1 second, right? So therefore the time between the two cars is actually from the starting point. The time that there was no car on the road was only zero point 0.1 seconds. So it's a very short, it's not enough for the truck to turn. The next car came in 4.9 seconds. So the total up to this point is now 4.9 plus point 1 is 5 seconds, right? So this 4.9 gap is not enough for the truck to turn. And the next car came in another 5.1 seconds. So total time elapsed up to now is 10.1, right? But the truck cannot turn during these two vehicles because the time between them is only 5.1. The truck needs at least 10 seconds. So the next car came in 2.4 seconds, and the next car came after that in 1.6 seconds, and the next car came after 7.9 seconds. So any of these gaps is not enough for the truck to turn, right? So like that, the next one was 2 point, the time between the next car and the previous car was 2.3 seconds. And then came a long period with no cars of 12.8 seconds, right? So this time was enough for the truck to turn because it is more than 10 seconds, right? So therefore, the total time by the end of this time is 37.1 seconds. So therefore, in this case, I'm going to take the time for the truck to wait. The time for that the truck driver had to wait until he can turn is 37.1 seconds. So that is one possibility. One possibility. Right? The vehicle can turn in 37.1 seconds. I'm taking the time at which the turning the possible time is over at the end, not the beginning. Right. So if you repeat this, you will get a different times between cars, and therefore, whenever you get uh, interarrival time, that means the time between cars to be greater than 10 seconds. At that point, the truck can turn. That's another possibility, right? So we can look at what other possibilities will arise like that. What are the other possibilities if the data are coming from? That means time between cars are coming from an exponential distribution with rate 1 over 3, right? So this is one value, one possible value, 37.1. So if I look at another one, that the total time until the truck can be turned will be some other value. If I look at another possibility, then in that case, the total time until the truck is turned will be another time. So like that, I can generate the data like this from exponential 1 over 3 distribution until I get a gap where the gap size is greater than 10. Once the gap size is 10 greater than 10, I stop generating exponential data and then find out the total time until the end of that period. So that will be one of the possible values for my total time. And then repeat again from starting from zero, assuming that I am starting from zero, generate exponential observations coming from exponential distribution with rate 1 over 3 until the time value, right? Exponential distribution is giving me the time between cars. So until I get a value greater than 10. Once you get a value greater than 10, then you look at the total time up to that point, including that, and then that will be the second total time possible. Like that, I will do this about 10,000 times so that I will have about 10,000 total times that the truck driver has to wait until he can turn uh, truck, right? So these are 10,000 possible values under this procedure, right? So therefore, if you take, say, for example, t to be the total time, so t is a random variable. In this case, t is equal to 37.1. In another situation, t will be some other value, t will be other value. So t is a random variable. The question is asking the median of that random variable. So once you have about 10,000 possible values for capital T, then you can get the median of those values that will give you an approximate value or the actual answer that we will get for this question if we solve this problem theoretically, right? So, but here the question is asking us to write down a program and then get the answer. So this is the procedure that I have to build into the R code. So this is what I have written down. You can understand this. I will go line by line. First of all, I say lambda is equal to 1 over 3. That is the rate parameter for the exponential. I am going to generate 10,000 values. That is, I am giving as n. And then I'm going to record this turn times. That means the total time that the person has to wait until a turn can be made. The truck driver has to wait until the truck can be turned. So that is, I'm going to, first of all, keep it as an empty vector, right? So I'm going to have 10,000 values at the end in this vector. So what I'm going to do is I'm going to do a for loop for I from 1 to n, right? So what I do is, so this is one, I'm going to look at the total time in one possible scenario. So at that time, I'm taking total time at the beginning, total time to be 0. And then I'm going to repeat generating exponential observations from this distribution with lambda equal to 1 over 3 until I get a value greater than 10. Right. So repeat this process here. So the values come from exponential distribution. I call it gap between the cars. So gap, first of all, generate a exponential random number, one number with rate equal to this lambda. And then at that point, the total time will be initial value 0 here plus the gap. And then we check whether this gap is greater than 10 or not, right? So gap is greater than or equal to 10. If gap is greater than or equal to 10, we can stop it there. And then at that point, my total time, the turn time will be equal to total time. If it is not greater than 10, then again, it will go here and generate an observation, right? Where is that? Yeah, it generate here, right? Because we are within that loop, within this repeat, right? So generate another exponential number. At that point, calculate the total time with that one. But again, check whether the gap is greater than 10. Otherwise, do this again and again until you get a gap from this random number generator, which is greater than 10. If that happens, then go out of the repeat loop. At that point, you have a value for the total time. So in that case, the first total time, which I call the turn time, the first value of that, I is equal to 1 in this case, it will be that total time, right? So that's giving me only one turn time in that case, right? Like 37 point something that we had in my example earlier. So I have to do it again. So now I equal to 2. At that point again, starting from total time to be 0, right? So this is a new procedure, new generation starting from 0, right? So repeat this until you get a random number greater than 10. Once you get it out, go out of the repeat loop. And then at that point, total time will be some value. Put that total time as the second value of turn times. So I is equal to 2. So turn times within square bracket 2 is equal to that total time. So that will be then repeated this thing again and again and again using the for loop n times where n is 10,000. So at the end of this loop, this turn times will contain 10,000 possible turn times. If the gaps are coming according to the exponential 1 over 3 distribution. So at this point, I can calculate the median. I can calculate the median. We move this to the up here, right? So M I calculate as the median of turn times. Usually this will be there will be a lot of decimal numbers. Therefore, I round it with to one decimal place, right? In addition to that, actually, I have drawn the histogram just to see what kind of turn values, what is the distribution of turn values also. Uh, this picture shows that histogram. So this is the histogram of 10,000 possible turn times when the process is going under that mechanism. That means the vehicles are coming, cars are coming, the gaps between the cars are exponentially distributed with 1 over 3 seconds, and then rate, of course, not 1 over 3, in that case, per second, right? But value is 1 over 3. And then whenever the time observation is greater than 10, you stop and then look at the total time and so on. So this is a histogram of 10,000 such values. You can see that's like a like a gamma, sorry, like an exponential distribution again, but it may not be exactly exponential, but it's a very positively skewed distribution. So from that one, I have already got the median from the previous set of commands here. I have value for m. I have drawn a vertical line at that value, right? So therefore, there will be 50% of the area below this, and then the total of this again is 50%. So this is the median. So median time required to make a safe turn, which is equal to m, is equal to 62 seconds according to this simulation, right? If I run the simulation again, the answer might be 61, 63, like that, around this value, because the random numbers that are generated will be different and each in each simulation. But it's roughly going to be 62 seconds, right? So that means the truck driver will have to uh, wait on average. The average in this case means the median, about 1 minute, right? Because in this case, because the wait turn times is very highly positively skewed, the median will be a good measure of the average than the mean, right? So therefore, if you calculate the mean will be somewhere to the right actually. So that's not giving you the good representation of the average in this case, because the distribution is positive. But here, uh, out of all possible turn times, 50% of them are below 62, 50% are above 62. Right. So that is how we can solve that problem. Okay, so now let us look at the second problem. This is example 2.18 from the book. Second example for this lecture. So it's called bathroom break. The number of customers arriving at a bank per time t follows a Poisson lambda t distribution. P within bracket lambda t means in this case Poisson distribution with rate lambda t, right? So here lambda is where lambda is the rate of occurrence of flow per unit period of time. Whatever the unit period is, depending on the question at least, and the actual values that you are looking to look at later on. But if lambda is the rate per unit period of time, that is on average how many events are occurring on average, how many events are occurring in a unit period of time. So if we are looking at the number of arrivals, number of events in t period of time, in that case, number of arrivals will be Poisson, but the rate will be now lambda times t. So that's why it says where lambda is the rate. It if the bank teller just served a customer and needs to take a bathroom break, right? So he has just finished with the one customer. Now he has to go to the bathroom. What is the distribution of time until the next customer walks in? That is the first question. Second one, does he or she have enough time to go to the bathroom if she needs 5 minutes and two customers arrive every 10 minutes on average? Right. So if two customers arrive every 10 minutes on average, and if the person needs 5 minutes to go mm, 5 minutes to go to the washroom, uh, will that be enough to come back before the next customer comes? That's the question. Right. So the first question, what is the distribution of the time until the next customer walks in? Right. Now, here the question is asking the time between arrivals. So the customer has already finished with one customer. So what is the time until the next customer comes in? That is the question. So that is the same as time between events, which we call inter-arrival times. Inter-arrival times. So there is a famous result related to the Poisson distribution. I have mentioned this before in my one of my several classes. If some events are occurring according to a Poisson process, then the interarrival times, that is the time between events, will have an exponential distribution. Right. To be more specific, suppose, for example, events are occurring. Usually these events are occurring, one event occurs, and then after some time another event occurs, after some time another event occurs, and so on. So that's what you call a Poisson process. If the number of events in a given period of time has a Poisson distribution, then we say this process is a Poisson process. In a Poisson process, the time between, if the Poisson process has rate, say, lambda, right? Let's consider the time as 1 unit, right? If the number of events per unit period of time is Poisson with rate lambda, then the time between two events will be exponentially distributed with rate lambda. In that case, the time will be in unit time periods. Unit time periods. Time mentioned in unit time period will have exponential distribution with rate lambda. Right. So that is the answer in this case. Generally, in this case, if you are considering lambda t, because you are considering t period of time. So what is the distribution until the next customer walks in? It's going to be an exponential distribution with rate lambda, right? We don't know what the t is. Whatever the t is going to be random. T will have exponential distribution with rate lambda. We can actually prove this result. So in order to prove this, let us assume that the number of arrivals in this particular example, number of arrivals in t period of time has a Poisson lambda t distribution as given in the problem, right? So in that case, lambda is the rate per unit period of time. We are considering t unit periods, t number of unit periods. Now let t be the time until the next customer walks in. Suppose the one customer came, and then we are looking at the time until the next customer walks in. Right. So let's in order to find out the distribution of this capital T, the distribution of the interarrival time, we will first derive the cumulative distribution function of capital T. Right. So by definition, the cumulative distribution function of capital T, evaluated at simple T, is probability capital T less than or equal to the simple T. But I can write down that as 1 minus the probability T greater than simple T. Why do I write down like that? Because I can write down this probability in terms of NT, because I know the probability mass function of NT. Therefore, now I will be able to get some expression for this in that result. That's why I'm writing. Now notice that T is the time until the next. So suppose, for example, the previous customer came at some time. So from that time, we are now measuring time. So the time that the previous customer left, we can consider as 0 again. So from that, we are considering the time until the next customer. So the event that T, that time greater than some specific value simple T, means time between 0 and t, there has been no arriving. Right. So therefore, this event that capital T greater than simple T is equivalent to the event that nt is equal to 0. Nt is the number of arrivals during t period of time. Right. So if the number of arrivals during the t period of time is equal to 0, that means the next customer will come after time t, simple t. So therefore, capital T will be greater than simple t. On the other hand, if the capital T is greater than simple t, there has been no arrivals from 0 to that point. Therefore, nt will be equal to 0. So therefore, the probability of this event we can find out using in terms of the probability regarding nt, right? So this event, capital T greater than simple t, is equivalent to the event that nt is equal to 0. Therefore, the probability that t greater than simple t is equal to the probability that nt is equal to 0. So that's what I have written down here. So coming from AFT and this expression. But now this part I can write down as probability nt is equal to 0. What is the advantage of writing that? Because I know the distribution of nt, right? So therefore, I can get the expression for this expression, this probability, right? The probability nt is equal to 0 is given by e to the power minus lambda t. You can easily get because nt has a Poisson lambda t distribution, right? So let me write down that quickly. Uh, so probability nt is equal to some n is given by e to the power minus lambda t to the power n divided by factorial n. Right? So what I need is this probability nt to be equal to 0. So this has to be 0, this has to be 0, and this has to be 0, and therefore the answer will be just e to the power minus lambda t. So that's what this is. Right. So when you substitute that, I have mistakenly written down the same thing again. But now I have an expression for the cumulative distribution function of capital T. It may be difficult for you to identify the distribution, name of the distribution for this one. Therefore, we will look at the density function because we are more used to the density function. So in order to get the density function, what do we have to do? I have to differentiate the cumulative distribution function with respect to t. Then I get this expression. So the density function of capital T evaluated at simple t is equal to lambda e to the power minus lambda t. And you will now recognize that this is actually the exponential distribution with rate lambda. So therefore, it shows that if nt, number of events, number of arrivals during t period of time has a Poisson lambda t distribution, then the distribution of interarrival times is exponential with rate lambda. So that's what the answer to the first part is. Right? First part asks what is the distribution of the time until the next customer comes. Right. And now let us look at the second part. Does he or she have enough time to go to the bathroom if she needs 5 minutes and two customers arrive every 10 minutes on average? So if two customers arrive every 10 minutes, what is the rate per minute? Rate per minute is 2 divided by 10, that is 0.2, right? We are looking at 5 minutes here, right? This person wants 5 minutes to go to the bathroom, right? So if you consider 5-minute period, in that case, the rate will be 5 times 0.2, lambda times t. Lambda is equal to 0.2 and then t is equal to 5. So that will be equal to 1. So the number of arrivals during 5 minutes will be Poisson with rate 1. The question is, what is the probability? Now he will be able to come back from the bathroom before the next customer comes if the number of customers arriving during 5 minutes is 0. That will be the case. Right? So we are interested in finding the probability that n5, right, n within bracket 5, right? And t here is 5 seconds, 5 minutes, right? N5 is 0, right? Where N5 has a Poisson distribution with rate 1, right? So we can easily find out that probability. That is one method to answer this question. There is another method. We will discuss both. So the method one, we look at N5. We let N5 be the number of customers that walk in during 5 minutes. Since the rate of arrivals per 10 minutes is 2, the rate of arrivals for 5 minutes is 1. Therefore, N5 has a Poisson 1 distribution. What we are interested in the probability N5 is equal to 0. We can find out that easily using R. Probability N5 is equal to 0 can be obtained by d Poisson 0, 1. Right? D Poisson gives you the density, or in this case, actually the mass function, evaluated at value 0. That is the probability that N5 is equal to 0. The rate comes as the second argument. So the answer is this. So there is a probability of 0.36 that he will be able to come before the in 5 minutes, and but there will be no customers during that period of time, and there will be no waiting for any customer in that case, right? So that's the one way to look at it, right? The probability that the N5 being equal to 0. We can also answer the same question by looking at the time, T. So let's say T is the time until the next customer arrives, right? So he has just finished with one customer and then he goes to the bathroom. So let's suppose the time until the next customer is capital T. If that T is greater than 5, there will be no problem that the person will come from the bathroom before the next customer comes. So we can find out what is the probability that T greater than 5, greater than or equal is okay, because in this case T is a continuous random variable. So we need the probability T greater than 5. So what is the distribution of T? As I told you, the lambda in this case, the lambda is the rate per unit period of time, where the unit period here is 1 minute, right? Since the rate of arrivals is 2 per 10 minutes, it is 0.2 per minute. Lambda is equal to 0.2. So therefore, T will have an exponential distribution with 0.2, rate equal to 0.2, lambda is equal to 0.2. So the question is, what is the probability T greater than 5? We can find that also using R, because probability T greater than 5 is equal to 1 minus the probability T less than or equal to 5, which can be found as 1 minus PEXP, that is the cumulative probability of the exponential distribution evaluated at 5. Rate is equal to 0.2. And when you simplify, you get the answer, this answer. You can see that from both ways, you can get the same answer. In this case, we got the answer by considering the number of arrivals. In this case, we have got the answer by looking at the time between events. Right. Okay. Now we will look at another example. That is, this is example 2.19 in the book. It's called earthquake occurrence. 3 seismological active regions, namely Taiwan, China, and California, have different patterns of earthquake occurrence. In particular, certain author named Wang and Co, both I think, 2 authors, confirmed that the interoccurrence, that is time between 2 consecutive earthquakes, nearly follows an exponential distribution with scale parameter for the 3 regions, 2465, 649, and 1131, respectively. Carefully notice that they are the scale parameters, not the rate parameters. And the rate parameter, usually with the exponential distribution, we mention the rate, lambda. Rate is equal to 1 over scale. So therefore, once you know the scale, therefore you can find out rates. So in this case, We know the three distributions of interarrival times of earthquakes in the three regions. All of them are exponential, but with different rates. Find the median and third quartile in years. I now notice that these are given in days actually. It's not mentioned here, but it has to be days. It cannot be years. These are in days, but the question is telling find the median and the third quartile in years. So you can find out first the median and third quartile in days and then divide by 365 to find out in years. The second part is compute the probability that no earthquake occurs within 1 year after past quake. Right. So that means what is the interarrival time is greater than 360 less than within compute the probability that no earthquake occurs within 1 year after the first quake. So that again can be solved in two ways. Either to look at the number of earthquakes within 1 year to be zero, or you can also look at the time until the next earthquake, let's say T, what is the probability that T greater than 365 days? That you can apply both ways. So let's look at the first one. Depict the three densities. First of all, I have to draw the three densities, find the median and third quartile in here. So I have written down here some codes. First of all, lambdas, the rates, I calculate lambda 1, lambda 2, lambda 3 as 1 over the scale values, given scale values. And then when I want to draw this on the same graph, I need to know what are the suitable values for x, right? Because these three distributions are different, but I want to draw all of them in the same graph. Therefore, it's better to take a suitable range for x values so that I can put all three graphs in the same, all three curves in the same, all three densities in the same distribution. So what I did for that is actually I found out the 99 percentile, 99.999 percentile, not the percentile actually, percentile is 99.9 percentile for each of these distributions, right? So this K1 is the 99.9 percentile for the first distribution with rate equal to lambda 1. K2 is the 99.9 percentile for the second distribution and third. And then what I did was I found out the maximum of the three values. So K is equal to maximum of the combination of K1, K2, K3. So I will take this K to be the maximum value in my X range. And then I will calculate the density on about 100 values from 0 to that K. And then I can connect them and draw. That's what I'm going to do. So first of all, I take some X values. I create X values using the command sequence from 0 to this K. And I'm going to create about 100 values between 0 and K. So that's my, I have 100 X values. At each of those X values, now I calculate the density of exponential distribution. I call them D1, D2, D3. So this D1 contains 100 density values calculated at these X values with the rate lambda 1. D2 similarly, D3 similarly, each has three values. And then when I want to draw all these three curves in the same graph, I can easily use the function matplot. So mind the matplot here, the x values are the same. So therefore, I can use just one x here. Otherwise, you'll have to, for example, if you have calculated these three densities at three different x vectors, then you have to combine those. C bind, then x1, x2, x3. But here I'm using the same x. Therefore, it's enough to say x. But the y values have to be combined as a vector. So I say C bind D1, D2, D3. Right. So put them as columns of a matrix. And then I'm going to draw them with the dark line without any dots or dashes, right? So LTY equal to 1 means without any dashes or dots, what you call it. And then I want to have a little bit wide curves, otherwise it's not very clearly seen in this picture. And then I want to use three different colors, one, two, three. One is black, two is red, and three, I think, green or blue. And then I want to also put a legend to differentiate these three things. So then I use the command legend, and then I have to tell where the legend, I want legend to appear. I want the legend to appear at the top right corner. And then what are the things that I want to mention in the legend? Here the legend, and then legend again inside as the function name is legend. And there is an argument called legend also in that. So in that one legend, these are the actually labels that I want to give for this three things. So I say I want the first one to be Taiwan, the second one to be China, and third one California. And then I want to change, otherwise it will just put X as the X label, but I want to give a more meaningful label. So I say X lab is equal to X equal to days after major earthquake. So these are the days between, right? And then Y lab is the density. So therefore I call it Fx. And LTY, I'm using again the same line type. And then colors 1 to 3. I have to mention, otherwise the colors that I mentioned here and the line type I used here will not count here, right? So therefore the line type has to be the same as the in the graph matplot, and the colors have to be in the same colors in the legend also, right? So then when I do these ones, I get a graph, and then in addition to that, I calculate the medians of each distribution. So median can be obtained using, if median is a quantile, so I can get the quantile by using QEXP command. So median 1 for this distribution is the QEXP at 0.5, that is the 50th percentile, right? So lambda, so this will be in days. In order to convert into years, I divide by 365 and do the same for the other two also. So then I put all those three things as a vector, combine these things, because then I want to later on prepare a table of these things, right? So then it has asked us to calculate the third quartile also. These quartiles are also quantiles. Third quartile is the 75th percentile or 0.75th quartile. So therefore, again, we can use QEXP, but now a 0.75 quartile, right? Quantile with lambda 1, lambda 2, lambda 3. These will be again in days. So to convert this, I divide by 365, right? And then I put those values also into a vector, right? And then it is asking us to calculate what is the, compute the probability that no earthquake occurs within 1 year after the past quake. Right. So here, because I already know the distributions as exponential distributions, what I'm going to do is I'm going to calculate the probability that the time between earthquake is greater than 365, right? So that is equal to 1 minus the probability time greater than and less than 365. So therefore, the first probability is 1 minus PXP 365 lambda 1. PXP gives you the probability T time less than or equal to 365, right? So this is therefore 1 minus, what we need is the probability T greater than 365, but that is equal to 1 minus the probability T less than or equal to 365. So that probability less than or equal to 365, you can get using PXP. So you get the three probabilities similarly, and I put those three probabilities as a vector again. Then I'm creating a data frame using those three medians and those three 75th percentile or 0.75th quartiles, third quartiles, and then these probabilities as three columns in a data frame. I call it output. Then when I print this output, I can see those three things as a matrix. Right. So these are the three graphs that I get by using the matplot command. Right? So you can see that the distributions, of course, all are exponential, but they are quite different distributions, right? So here I selected that Q 99.9 percentile. So therefore, all three actually shows up to a reasonable range. But if I wanted, I could have chosen a little bit more. Then you can see that all coming close to zero a little bit when it goes to when it goes right to some larger number, right? So these are the three densities. So what you can learn from is here is just a method to draw several graphs in the same picture using matplot. And these are the answers that I got for the three cases. Median waiting time for the next until the next major earthquake, right? Time until the next major earthquake in years, right? So 4.6, 1.2, 2.1. So this is uh, Taiwan, the other one is China, the other one is California. So these are the Q3 values. This is the probability that there will be no earthquake during the next year, right? So there will be a 0.86 probability. There will be no earthquake in Taiwan, and this is the probability for China, right? And this is the probability for California. But the answers were given in the book also. I noticed that these Q3 values given in the book are actually not correct. So there has been something wrong in the book. Other values are correct. Median values are correct. And the P values are correct. But these values are not correct. So, I mean, I have these things correctly, but these cannot be these values. So there has been something wrong here. Right. Now, let us look at the next example. This is the example 2.26 in the book. Relationship between Gamma and Poisson distribution. We have already seen the relationship between exponential and Poisson distribution, right? If some events are occurring according to a Poisson distribution, and therefore the process, if you consider them as a process of events occurring one after the other, it's called a Poisson process. If the events are according to a Poisson process with some rate lambda per unit period of time, then we have shown that the time between events is exponentially distributed with rate lambda that we have already seen. Now, suppose, for example, you look at the time between two events, so that will be exponentially distributed random number with a rate lambda. Then from that, again, you can, if you look at the time until the next event comes, that will be again an exponential random number with rate lambda. From that point, you can look at the time until the next event comes. That will again be an exponential random number from the exponential lambda distribution, right? So like that, suppose you look at n events, right? So each value, that is the time between two events, will be a random number coming from the same exponential distribution with rate lambda, and these observations will be independent of each other. So therefore, you will have n independent and identically distributed exponential random numbers with rate coming from exponential distribution with rate lambda. Now, suppose you want to look at the total time for this n events, total times for this event. That is called the waiting time until the nth event, waiting time, right? So that waiting time until the nth event from some specific event after some specific event, from that we are waiting until the nth event occurs. So the total time up to that will be the sum of IID exponential random numbers, random variables. And we know that sum of n IID exponential random variables has a gamma distribution. Gamma distribution with shape parameter alpha is equal to n and rate parameter lambda will be the same as the rate parameter of the exponential distribution. Right. So that is what we mean by the relationship between gamma and Poisson distribution in this case. Right. So you are considering a Poisson distribution and then looking at the wait in time until the nth event occurs. And that will be a gamma distribution. If the Poisson process has rate lambda per unit period of time, then the waiting time until the nth event will have a gamma distribution with shape parameter n, that is the number of events we are looking at, and rate parameter will be the same as the rate parameter of the exponential distribution. So it's asking us write a R code that confirms. There is a typing error because I copied it from the book and then I think there was a space between that and I forgot to erase it. The relationship between the Poisson and gamma distribution through simulations. Right. So plot the empirical CD of the number of event occurrences until n and superimpose the actual gamma CDF on the same graph. Right. So what is asking us to do is so generate data from Poisson distribution with some known lambda, right? And then generate those numbers until you get n interarrival times, right? So starting from 0, so once the first event occurs, right? So then there will be a certain time and then second event, third event and so on. So then look at the time up to the nth event. So how do we do this? One method we can look at is actually we can divide, say, for example, one day into, say, 1 minute periods, say, right? So from some starting point, then the time, how many time periods will be there? 24 times, 60 time periods. Then what we can do is, this is only just one method we can do, right? We can generate, according to whatever the lambda we are going to assume here, we can generate the number of events occurring in the first minute, right? So you get just a random number from the Poisson distribution with rate some lambda. Yes, we are going to fix a lambda value later on. And then take another random number, Poisson random number from the second, the same with the same rate, and take that as the number of events occurring during the second minute. And like that, generate data for the whole day. Then, of course, you will have large number of events. For example, in the first minute, maybe 0 events. In the second also, maybe 0 events. In the third one, maybe 2 events. In the fourth minute, maybe again 1 event. And the fifth, maybe 0, like that. So find out where the nth event has occurred. Suppose n is, for example, 300. We are going to look at the total time up to 300 events. Right. So maybe 300 event occurs in the 100th minute. It's possible, right? So you find out the cumulative number of events one by one, adding every minute, and then find out where are the 300th one will be, right? So before that minute, their cumulative will be less than 300, but in that one, within that one, the cumulative at the end of that minute, cumulative will be more than 300. So therefore, the 300th one will be occurring during that minute. So I take the time up to the 300th event from the beginning to be the end time at that period, minutes. Okay. So that will be one possible value for the waiting time until the 300th event. And do this thing again, right? Again, generate random numbers for the first minute, second minute, third minute, and so on. Find out where the 300th event occurs, and then get the total time up to the end of that time period in that minute, right? So that will be my value for the time, waiting time until the 300th event. That is my second possible value. Like that, you can do this thing again and again and again about 10,000 times. Okay, you can find out 10,000 possible values for the until the 300th event occurs when the number of events occurring in a given minute has a certain exponential, certain Poisson distribution. So once you have those 10,000 values, of course, you can find out the empirical cumulative distribution function. We have already discussed about this thing in previous lectures. One of the previous lectures, we learned how to draw the cumulative distribution, empirical cumulative distribution function. And we have learned that empirical cumulative distribution function is an unbiased estimator for the actual CDF and so on. So that's what we are going to look at actually in this case. We can draw the actual CDF and the empirical CDF and then compare those two. Those two should be very close, right? So that's what we are going to do here. So here I have first explained the relationship between Poisson and gamma, which I have already done, but let me go through again. So if nt is the number of events during a t period of time, and if lambda is the average number of events or the rate per unit period of time, then nt will have a Poisson lambda t distribution. Then the waiting time until the first event, say T1, will have an exponential lambda distribution. And similarly, from that point on, waiting time for the next will be again exponential. T2 will be exponential with rate lambda and so on. So if you look at the total time until the nth event occurs, will be, let's denote it by Wn. Wn will be equal to T1 plus T2 plus up to Tn. Each T1 is the inter-arrival time. Wn is the waiting time. All those T1, T2, 3 up to Tn IID exponential lambda. Therefore, Wn has to be gamma n lambda, gamma n lambda. We can easily prove this using the moment generating function technique, right? We have discussed about this method and we have looked at examples also. So I encourage you to prove that. So therefore, lambda n has a gamma n lambda distribution, right? So that is the way that is one way to explain that. Or we can explain it using events and the probabilities also, right? So suppose, for example, Wn, we can show that the probability that Wn less than or equal to some value t is the same as that the probability nt is greater than or equal to simple n, right? Here n is a fixed value, simple t is a fixed value, right? So let us consider Wn less than or equal to t, right? Wn is the waiting time until the nth event occurs. That will be less than or equal to t if and only if the number of events during time period t period of time is greater than or equal to n, right? So therefore, this event Wn less than or equal to simple t is the same as, is equivalent, not the same, it's equivalent to the event nt is greater than or equal to simple n, right? Nt is the number of events in t period of time. If that is greater than or equal to n, then the time up to the nth event will be less than or equal to simple t, right? So therefore, the probability of this event is equal to probability of this event. That is another way to explain the relationship between this gamma gamma distribution and the Poisson distribution. So here is my program to find out 10,000 waiting times, right? I have written down a function. I'm going to consider this. These are the default values that I'm going to consider. N equal to 300, lambda equal to 5. And I'm going to consider 24 times 60 values, 60 minutes. And in each minute, I'm going to find out number of events. And so I will do it for one day, and then I will do it for another day. I'll do it for another day like that for 10,000 cases. Right. So first of all, I'm going to create a vector called times, right? It's going to be a length with length n sim 10,000 values, right? Okay, so that's I'm going to store the total wait in time in one session, and then again another value in time, right? So here what I'm going to do is for I in 1 to n sim, that is a for loop. First of all, take x R poise this number of values. So for each minute in a day, I'm going to generate a Poisson random number with rate lambda equal to lambda, right? And then I'm going to find out okay, what is the total number of events by the end of the first minute? What is the total number of events by the end of the second minute? What is the total number of events by the end of the third minute, and so on. Then you can find out that using the cum sum function of x, cum sum x, and I call it Cx. And then I want to find out now among these cum sum, where are the 300th, n is equal to 300, where the 300th event has occurred. Right? That can be found out using this one. So first of all, what I do is I get the which Cx greater than or equal to n, this part here, right? This command gives you which Cx values, right? Or the fifth value, 10th value, 15th value, and so on. Which values? Which Cx values are greater than or equal to n, right? Cx, remember Cx contains the cumulative sum of x. So which of those Cx values are greater than 300, right? So there will be some point, and after that, actually, each point after that will be actually Cx will be greater than 300. So therefore, this which Cx greater than or equal to n will give me a vector of values. For example, 100th value, and then after that, every Cx value is greater than 300. So what I want is where is the first minute, which minute the 300th event occurred. So therefore, if I look at the minimum of this vector, that will give me the time, right? Time until the end of the minute in which the 300th event occurs, and I put time I to be that value. So remember, I have created a time vector, empty vector with n-sim number of values. So in that vector, the first value will be this when I is equal to 1. And then I do it again and again and again, n-sim times. So thereby I will have 10,000 uh, waiting times until the 300th event. Then, of course, I can plot uh, these things. I am using the ECDF function. There is a function called ECDF to draw the empirical cumulative distribution function of these time values, right? So for that, this is the command that you have to use, plot, and then ECDF time will give you the empirical cumulative distribution function. But in addition to that, within plot command, we can give some other arguments. What is the main title I want to be? I want to have, what is the X lab I want to have, what is the Y lab, and whether I want the vertical lines to be put in. Because remember, this is going to be a discrete step function, right? So if I want, I can have vertical lines at these steps. Otherwise, I don't want to have them. So in this case, I'm asking them to put the vertical lines also. So that's why verticals equal to true. And then do points means connect the points uh, uh, vertically, not by points, but by lines. So that's do points equal to false. So that will give me the cumulative distribution function, step function. And then I want to draw on top of that the actual gamma density function, sorry, CDF function, right? So what I will do is at each of these uh, I think I made a mistake. Okay, what is X here? P gamma. P gamma actually gives you the cumulative distribution function, actual X. Uh, yeah, I have forgotten to type here because I have to now get some sequence of X values to calculate the density function. No, actually, when I say uh, yeah, this what this function is doing is actually adding the curve to the already available graph. So it will be automatically selecting suitable x values because it's adding to this graphs. This graph has been already drawn. Therefore, the computer knows what x values. What are the x values for that graph? So by this curve, this curve function, it will automatically take those x values to calculate the cumulative distribution function of the gamma distribution with say p equal to n and rate t equal to lambda, right? And then say add d equal to 2 means add it to the previous graph and line width to be 2 and line type to be 2 that is dashed lines. And then include the legend, right? Here I'm asking to put the legend at the bottom right because the graph is going to be going up. Therefore, the bottom right will be empty. Therefore, I'm going to put it there. And then legend. And then the first graph is going to be empirical CDF. The other one is the actual gamma CDF. So line types will be 1 and 2. This one is for the line, this one will be line type 1. Here I have asked for this to be line type 2. Therefore, line types will be 1 and 2. And line width, I'm going to also change 1 and 2. If I want, I can have the same width. But here, the CDF, empirical cumulative distribution function, line width will be 1. The other one, line width will be 2. And BTY equal to N means don't put a uh, 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 frame around the graph, right? I want to remove the frame then to make it right. Otherwise, it will put frame. No, the BTY equal to N actually, what that does is actually it removes, it doesn't put a frame for the legend. Otherwise, there will be a frame for the legend that will make sometimes this will be a little bit congested. So therefore, it's better to remove the legend, the box around the legend. So this command here does that. BTY is equal to within quote N. Right. So this graph is produced by this. You can see that actually this graph, the empirical cumulative distribution function is above, uh, sorry, below the actual density function at each point. So that's not a very good sign actually. That the reason for that is actually because remember we are getting the time to be time of the 300th event to be the time at the end of the minute where the 300th event occurred. But actually, the 300th event may have occurred within somewhere in the middle of that minute also. But there, we have no way to find out what the actual place of that minute is. What we take is as at the end of that minute. So therefore, the values that we are generating are not the actual values that would have been coming from the actual process. So there is a little difference there. That's why this empirical cumulative distribution function is going to be is below the actual CDF always. Otherwise, this would have been cutting off this one. This would have been around if we had actual observed times. Then if we draw the empirical cumulative distribution function for that, that would have been around this actual density. You have seen that in one of in our previous examples. We had the actual data generated from the known distribution and then drawn the actual CDF and actual ECDF. So that is actually is a unbiased estimate. But this picture doesn't show that it's unbiased coming from as an unbiased estimate coming from an unbiased estimate. So that is the reason for that. Right. Okay. But then there was a question asking, no, that was the only answer, right? The only question. We have asked to draw it, yeah, superimpose the gamma CDF on the same bar, right? So we will look at one more example. This is example 2.27 called You Are Fired. You work at a college, at the college telephone board as an operator and step out for 3 minutes. The rule is that if you miss two calls in a row, you will be fired. Actually, when you say the rule is that if you miss two calls, not exactly two calls, that means actually two or more calls, right? If you miss two or more calls, you will be fired. That means if you cannot come back before uh, missing two or more calls, you will be fired. Assuming that calls arrive with a rate lambda equal to 2 per minute, according to the Poisson distribution, what is the probability that you will be fired, right? So how do we find out this? It's a very simple question. Assuming that the number of calls arrive during uh, number of calls arrive with rate lambda equal to 2 per minute, what you have to do is what is the probability of observing two or more calls in 3 minutes, right? That is the probability that you will be fired, right? If you get two or more calls during 3 minutes, you will be fired. So that's a very simple question. You know that number of calls per minute is equal to 2. Therefore, you are looking at 3 minutes. Therefore, if you consider the number of calls in 3 minutes, it will have a Poisson distribution with rate 6, 2 times 3, right? So let's say N is the number of events, number of calls that would come in 3 minutes. So N will have a Poisson distribution with lambda rate equal to 6. So the question is, what is the probability that N is greater than or equal to 2? You can easily find out that using R command, right? So let N denote the number of calls arriving during 3 minutes. Since the call rate is lambda is equal to 2 per minute, N will have a Poisson 6 distribution. The operator will be fired if two or more calls arrive while he is away. So therefore, what you are interested in, the probability that he will be fired, that is the same as probability N greater than or equal to 2, which is the same as the probability 1 minus the probability N less than or equal to 1. Right? So that you can obtain as 1 minus P poise 1 6. And that is going to be 0.98. So it seems that if you go out for 3 minutes, there's a very high chance that you will be fired, right? Almost 98% chance, right? Or the probability is 0.98, right? So that's the whole time that I have, roughly about 1 hour. Uh, Therefore, I will stop this lecture here. And then from next class, I will start chapter 3. Chapter 3. Chapter 3 concerns uh, multivariate distributions, joint distributions, and so on. Up to now, in chapter 1 and chapter 2, we were dealing with univariate problems, right? Distribution of a single variable and all the thing, expected values, variances, probabilities, so many things regarding single variables, and then transformations of those into again a single variable. In the next chapter, we will be looking at multiple variables together. So therefore, we'll be talking about joint distributions, covariances, correlations, and so on. right? Joint probability mass functions, joint probability density functions, conditional probabilities, independence, and so on. So that will also be an interesting chapter. So that is the end of this chapter 2.